Okay? So let's see. So f of x was equal to the square root of 2x plus 3. Right? So as a first thought, what's the domain of f? You mean negative 3/2 to infinity?
Yeah.
Yes?
Negative 2.
Sorry?
Would it be negative 2?
Well, think about what you have. You have 2x plus 3. This is exactly what I was talking about last time. You don't have to really just look at it and try and get the answer. The whole point is you can't have negative numbers under the square root. So what do? Well, we just write it out. Right? So I have 2x plus 3 bigger than or equal to 0. And now if all I have to do is just basically solve for x. So I'll have 2x bigger than or equal to negative 3, which means x is bigger than or equal to negative 3/2. Does that make sense? Okay. So, oh, it's not on? Okay. So now if I look at f composed with f of x, I end up with f of the square root of 2x plus 3. So it's just going to be the square root of 2 times the square root of 2x plus 3 plus 3. Right? So then what is the question?
Can you set that equal, can you set it, greater than or equal to 0?
So again, I guess maybe your dilemma would be what's the domain of this function?
Yeah.
Right? Well, as it turns out, the domain is actually quite simple. Why? Well, first of all, 2x plus 3 has to be bigger than or equal to 0, which means x has to be in negative 3/2 to infinity. Right? Assuming that that is the case, that x is here, do I have any additional constraints? Well, technically, I do, right? Technically, I would say 2 times the square root of 2x plus 3 has to be bigger than or equal to 0, right? But what is this actually saying? Square roots are never negative, right? Adding 3 to it surely doesn't make it negative, which means this will always be positive, as long as this square root actually makes sense. Does that make sense? And so the domain is negative 3/2 to infinity, right? Because this still has to make sense. Remember what we talked about? The fact that when you look at a composition of functions, the second function in your composition, that domain has to be taken into account when you come up the end, right? Remember, the last problem, bless you, the last problem we did on Monday was the one with 1 over x. And remember, we worked out all the algebra, and 0 didn't actually show up anywhere at the end. But you still have to keep track of the fact that 0 couldn't be possibly a solution, wasn't part of the domain originally. Does that make any sense? Okay. That's it? Yes?
In section 1.2, number 52, I didn't understand how to use the table to evaluate the expressions.
Ah. Well, it's just a game.
I don't understand.
So just think about the following. And I'm not going to reproduce the table because that's just going to take too long. But just think about the following. You have... Let me just take this thing here and actually say it correctly. For instance, if you look at, I don't know, part B, since I actually started writing G. G of f of 1. Well, what have I done in general? Like for instance in the previous problem. Remember what I said? I said f composed with f of x is f of f of x. And the next immediate thing I said is, well, what is f of x? Let me just put it in. Right? So this exactly shows up in problem 52. What is f of 1? What is f of 1? What is f of 1? 3. Much better answer. So that is just g of 3. And now what is g of 3? 2. Is everybody understanding this? Yes.
Okay, I understand this, but whenever we turn in homework, the day we turn in homework, we have a chance to go over the homework assignments and correct our answers. Is that what this is?
Yeah. Well, let me say this. Remember how we grade homework, right? You basically, like for instance, if you look at this particular homework set, you had 14 questions. And if you go later on, you'll find that 14 questions is actually probably short homework, throughout the semester. So out of those 14, usually you get graded like 3 or 4 homeworks, problems. And I'm trying to make sure that everybody understands how problems work. And so, and I guess again, probably because I got so sidetracked with the pretest last week, I kind of forgot to say this, I think. I don't have a problem spending 10-15 minutes before class, at the beginning of class, actually talking about homework. Clearly, there's no way I'm going to solve all your homework problems. But if you have like a problem that you don't necessarily understand how to do, I'd much rather you know how to do it than actually copy it from somebody that sits next to you, and just so you have the homework completed. Because chances are, again, if you look at this particular homework set, just looking at section 1.2, we had 4 or 5 different types of problems. Chances are you're not going to be graded on every single one of these types. So I want to make sure that you actually understand how to do them. So I'm not going to spend more than like 15 minutes because I just don't necessarily have that time. But I'm willing to spend 10-15 minutes on on a problem here and there in case you don't necessarily know how to do it. What I usually do is I actually keep track of the problems I solved in class, and I basically tell the grader not to grade those. So, because otherwise, what's the point of me grading you and copying from the board? Does that make sense?
Yep.
And I don't have to do this. I just figured this way you actually learn a little better about how things work. So, anyway. Okay. Since the camera's over there, I guess I'm going to have to ask you to move all your homework to your left, my right, because it would be easier to actually go collect it.
Is there a stapler up there?
There is no stapler, and as far as the first homework is concerned, I will let you slide. Starting from the next homework on, you're probably going to get penalized for not stapling your homework. I do have a stapler with me. Yeah, I know, it doesn't look like a stapler, but it actually is a stapler. Let me see. Did you break my stapler?
It's pretty easy.
Alright, 5 points off. Oh, I'm sorry. Apparently,
Come on, everyone.
a well-prepared man. We all have staples?
I barely broke Yeah, she's all better.
Thank you. All right, so any other questions? I don't know what other possible questions you might have, but I just figured I'll be nice and ask. Okay, so starting today, we're actually going to start calculus. So today we're going to actually start talking about limits, and we're going to start relatively slowly in the sense that as a first step, we're actually going to try to look at what a limit is and what exactly are we actually talking about as far as functions are concerned. So, let's see. The title of the section would be the limit of a function, section 3, 1.3. Chances are I'm probably not going to actually remember to write the title of each section, and sometimes they're actually very lengthy, so I'll skip that, but for now I'll just write it out. Okay, so I'm going to more or less follow, this is probably one of the very few situations in which I'm going to do exactly the opposite that I said I'm going to do on Monday, in the sense that I'm actually going to go through the examples, because well, I don't have a calculator with me, and I really don't want to spend the time to actually try and calculate all these values. So this is just kind of like, it's a lot easier for me to actually look in the table and kind of reproduce and explain to you what we're actually looking at. So example 1 says the following. Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Since it's Canada, we deal with meters, I guess. Find the velocity of the ball after 5 seconds. So, to some extent, by the way, I don't know, there's this, I guess it was an urban myth until, I guess the Mythbusters actually went and proved it, that if you drop a penny off of the Empire State Building, you can actually kill somebody, right, on the ground. I don't know if you've actually seen that. Yes, it worked. Yes, and so the point is, how do you figure that one out? One way of looking at that is what's the velocity of the object by the time it actually hits the ground, right? So this is kind of not necessarily that particular type of question, but it's kind of similar to that. The idea is we want to know what the velocity of the ball is after 5 seconds, which is something that actually could be very interesting, like as an actual real life problem. So how do we actually set things up? Well, as it turns out, a very, very long time ago, I guess not that long, but anyway, Galileo discovered a distance fallen by any freely falling object is proportional to the square of the time it has been falling. And so the idea is, if I denote s of t, the distance at time t, so here I'll draw a lovely picture here. Actually, I don't know what the CN Tower looks like, so I'll just make it look like that. The idea is you basically are thinking about dropping a ball from the top going down, and so the distance would basically be, this would be s of t, right? How much it actually traveled after a time. So Galileo discovered that s of t is equal to 4.9 t squared. Anybody took physics? Do you know why 4.9 t squared? No? Well, it's the force. Do you know what the acceleration of the gravity is? 9.8 meters per second. Right? And so the idea is you get 9.8 meters per second. It's actually 1/2 9.8 times t squared. So it comes up with 4.9 t squared. Okay, so this is all nice because this is actually telling you what the distance, so if you tell me, if you want to know how long did the ball travel in 2 seconds, well, you just put in 2 for t and you come up with it. However, our question is, what is the velocity? Okay, so the problem that we have with the velocity is the fact that we actually don't have a certain interval to actually talk about things, right? I mean, yeah, obviously if you're in a car driving, to Denver, well, all you have to do is just look in on your speedometer, and it basically tells you what your speed is, which is the same thing as velocity in that respective regard. By the way, do you know the difference between speed and velocity? Yes. Exactly. The velocity actually counts for direction. Speed does not. Right? Speed is actually the absolute value of velocity. But anyway, since we're talking about going in a positive direction, they would be the same thing. So the one thing we can do is we can actually look at the average velocity. And so the goal is to actually try and see what happens if I actually look at some sort of an interval of time and try to shrink that interval. See if I can actually come up with the velocity, because the smaller I get the interval, the more technically of an approximation I get. So how can I come up with the average velocity? Change the distance and change of time, right? So change in position divided by time elapsed. Does that make sense? Okay, so let's look at a table of data, and this is why I said I'm actually going to choose the example in the book, because it's a lot simpler to do versus actually trying to compute things. So if I look at a time interval, and I look at my average velocity, let's see. If I look at the interval between 5 and 6, this is going to end up being 53.9. Do you want me to write out how you actually come up with that? Just for this one, maybe I'll do. Think about this. The average velocity is going to be s of 6 minus s of 5 divided by 6 minus 5. Does this make sense? Now, let me just say one thing, because it doesn't actually portray here. And this is actually going to come back later on for our purposes. Does this look familiar? Think about s being a function. What am I computing here? The slope, right? Does that make sense? Now, as it turns out, for my particular function, that's not a linear function, so doing this doesn't necessarily give me the slope, but that's y2 minus y1 divided by x2 minus x1 is usually the slope between 2 points, right? And this is going to come back later on, and that's why I kind of wanted to bring things up. Okay, if I look between 5 and 5.1, I'm going to get 49.49. And I'll just skip one. Let's see, between 5 and 5.01 is 49.049. And between 5 and 5.001 is 49.0049. So the instantaneous velocity is defined at t equals 5, is defined to be the limiting value of these averages. And so the key idea is, when your interval gets smaller and smaller and smaller, do we notice a pattern as to what our value might actually lead towards? And the answer is 49 meters per second. Does this make sense? If you look at it, as I keep going, it gets closer and closer to 49, right? Well, we just witnessed our first limit. Now, as it turns out, trying to do this for every single problem in the book is surely not fun. But let's see. Let's look at an example of a function. So let's look at f of x equals x squared minus x plus 2. Okay? Graphically speaking, what we're looking at is, let's see, I'm going to more or less the question would be the following. What is the limit as f goes to 2, or as x goes to 2 of f of x? This is actually what we're going to try and come up with. And so the question is, as x gets closer and closer to 2, what is the value of f? Well, all we have to do is just basically trace it on the map. Now I'll show you this again. If I look at x and f of x, what have I done in the past, in the previous problem? I looked at the interval between 5 and 6, and I kept shrinking the interval and kind of looked at what the limiting value is going to be, right? Anybody has a thought as to what we're actually going to find? No? I am surprised. Yes? What is the value of f as x gets closer and closer to 2? 4, right? That's actually what we're going to see. Why are we going to see that? Well, because at x equals 2, f is in fact equal to 4. But there's a hidden idea behind this information, and it might seem like a weird question right now. You'll see in a couple of minutes why we're actually posing the question in this form. So let's see. If I start at x equals 1, f is equal to 2, and I'm just going to skip a bunch of these numbers. I'm on page 25, by the way, if you actually want to see the table. 1.99 is 3.9701. 1.999 is 3.997001. Everybody sees that as x gets closer and closer to 2, the value of f gets closer and closer to 4. Now, the most important property of limits is the fact that we're interested in the behavior of the function close to a point, but not equal to the point. And so the idea is, notice that I haven't actually put x equals to 2 here. Okay? The key idea is, as far as limits are concerned, is what happens as I get closer, so graphically speaking, as I get closer and closer to 2 with the value of x, what happens with the graph? Well, the graph keeps going up until it basically hits 4. Right? Is everybody seeing this? On a similar token, if I come from the other direction, by the way, this would not be enough to actually say that the limit as x goes to 2 of f of x is equal to 4. Why? Well, because I'm only coming from this direction. I don't know if coming from this direction is going to give me the same answer. And we'll see why. So, if I look at x and f of x, and now let's see, I start at 3, gives me 8. I go to 2.01. I have 4.0301, and then I have 2.001, and that'll give me 4.003001. So both of these coming from the left or coming from the right, and we'll talk more about what does it mean coming from the left or right. Both values get very close to 4, and so the conclusion is that in fact the limit is 4. So, conclusion, as x gets close to 2 but not equal to 2, f of x is close to 4. Is this making sense? This is the notion of a limit, and it might not be very apparent at this point. Why are we actually concerned with x getting close to a point but not actually equal to the point? But trust me, as we'll go through this particular section, you'll find out why we're really interested in this particular definition and not anything else. Alright, so this is the definition of a limit, so actually just let's actually make it a definition. We write lim x arrow a of f of x is equal to capital L, and say the limit of f of x as x approaches a equals L. So, basically just think about actually just reading it, right? The limit as f of x, the limit of f of x as x goes to a is equal to L. If we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a. And I should make this shorter, I write it out, but not equal to a. And again, that's actually the key part about things. So the idea about limits is the following. If what we're really interested in is actually the behavior of f near a, not actually at a, which basically says, if I am to actually look at a few graphs, so think about, let's see, let's say I have this function, this is a, this is capital L. What is the limit? Here, I'll write it next to it. What is the limit as x goes to a of f of x? Well, if we look on the picture, if I come from the left side of A, as I get closer to A, my graph keeps going up and it'll get closer and closer to L, right? If I come from the right, which means I'm going this way towards A, my graph descends until it actually hits L, right? Which basically means from both directions I end up with capital L. Yes?
That's the question. In what case would it not approach A coming from the other side?
I'm sorry, say that again?
In what case would it not approach A coming from the other side?
Not approach L, you mean, right?
Right.
Um,
Coming from the right to the left.
We'll see. Think about. Let's look at this particular function. What is the limit as x gets to a of f of x? So let me ask the same question. Let me write it out. The limit as x goes to a of f of x is equal to, and let's actually make, so f of x is defined to be this lovely line here, but when x is a, it's actually defined to be b. What is the limit as x goes to a of f of x? The answer is capital L. And this is where things, are starting to kind of come a little bit together, in the sense that we're interested in the behavior of f close to a, not at a. I don't care what the value of f of a is. Okay? So let's say this, let me just write it here. But f of a is in fact equal to b. Right? Because f of a, I defined it to be b. Is everybody understanding this?
Wait, wait.
Yes.
F of A isn't even on the line.
Yeah, I know. So what's the problem if it's not on the line? Again, the key idea is I don't care what the value of the function is defined at a. Actually, moreover, I could have my function not even be defined at a, in the sense that I could actually have my function, okay, f of a does not exist. Are you familiar with this notation, by the way? DNE, does not exist? Does not exist. Do you want me to write it out, actually? Because this would be the first and last time you ever see me write it out. So, do you want me to write it out? Okay, so f of a does not exist. So now the question is, what is the limit as x goes to a of f of x? The answer is L. Yes?
Is it kind of like a piecewise?
Yes, this would be kind of like a piecewise function. Yes. But it's not really piecewise because I guess it's the same piece. Right? But the point is, this, my graph is not defined here. Okay? The best case, you might wonder, you might ask yourselves, how would I ever see a function like this, right? I'm sure some of you already thought about that, right? No? Okay. Well, nonetheless, I'll show it to you anyway. X squared minus 1 divided by x minus 1. Do you know what the graph looks like?
Right there.
Not quite.
The intercepts of -1 and 1, which is an open circle 1.
Yes, but the difference is that this is actually x minus 1 times x plus 1 divided by x minus 1, which is x plus 1, but x cannot equal 1. Right? Everybody understands this? Again, this is, and I want to make this distinction because you might be tempted to just cross them out and say my function is x plus 1, but that is not what actually happens here. The point is, for you to be able to cross these two out, x cannot equal 1. Otherwise, you can't divide and multiply by 0. It makes no sense. Okay? So, if you think about the graph of this particular function, well, it'll just look like that. Does this make sense? So we actually just saw this type of a function, right? So now what is the limit as x goes to 1 of f of x? Well, as time passes, we'll learn more about these things. You want me to pick up a table and look at values? Say no? No, I mean, I can do that. I actually don't have a calculator, so somebody's actually going to have to take out a well, I guess for this one, you don't really need a calculator. So let's see. Let's play around. We start at 0.5. What is f of 0.5? 1.5. 0.75. What's f of 0.75? 1.75. 0.9. 1.9. 0.99. 1.99. Do you see where things are going? Okay, let's come back from the other direction. X, f of x. So how about I start at 1.5? What's f of x? 2.5. Okay, I'll skip the 0.75. How about 1.1? 2.1, 1.01, 2.01, and so forth. So what is the limit as x goes to 1 of f of x? Well, if you look at the tables I have, from both directions, they're both going to 2, which means my conclusion is that the limit is in fact 2. Does that make sense? Yes? Graphically speaking, because we have the graph, which means that we should be able to identify it quite easily, as I go to 1 from left, so would basically be this case of the table, my function keeps rising until it hits 2, or close to 2, right? From the right hand side coming down to 1, my function will decrease and it'll hit 2, right? Since both situations happen in the same time, my limit is in fact equal to 2. Does this make sense? Now, to answer your question, I didn't want to jump the gun and get to that first, but to answer your question, if I have a function that does that, say this is A, okay, A is a bad notation, so call this capital M and capital N. And let's baptize this A. We actually are witnessing something called side limits, in the sense that when x goes to A from the left, my graph traces up and it hits M. However, when I come from the right and hit A, my graph is going to be in the other branch and it'll hit N. As it turns out, it doesn't go to the same place, which means the limit as x goes to A of f of x does not exist. Is this making sense?
No.
What is the problem?
Is that because there's no closed dot?
No.
in?
Again, we don't care what the value of the function is at that particular point. We never do. The definition says the limit is equal to some value of L if I can get as close as I want to that point coming from either direction. So the point is, when I'm coming from the left, I end up at M. When I'm coming from the right, I end up at N. I don't end up in the same point. Okay? Questions?
Would you have two limits? Or just,
Sorry?
I guess you just don't have two limits. Just that.
We have something called side limits. And I'll get to that very shortly. Before I get there, I want to go through example 3. I guess I skipped example 2. I kind of made my own example. So example 3, and the reason why I'm bringing this up is because sometimes we need to find a tool to better figure out if a function has a limit or not. I mean, it was all nice for the previous function, for the only function that I actually drew here explicitly was, this function, x squared minus 1 over x minus 1, and I was able to graph it very easily, right? Now the question is, given a function, are you going to be able to graph it or not? And chances are, you probably won't. Like for instance, example 3 has a function of the nature of the square root of t squared plus 9 minus 3, all divided by t squared. Okay? So the question would be, what is this particular limit? So what we've done so far is we actually made tables, right? We said t goes to 0, so we're going to pick negative values of t and positive values of t, right? And we're going to come from both directions. Does that make sense? Okay, now notice I'm going to be sneaky about it, I guess, not necessarily sneaky about it, but the idea is t only shows up here as t squared, right? Which means either if it's plus or minus, it'll still be the exact same value, right? Which means we can actually take the table and put it together from both directions. So I'll have t, I have the square root of t squared plus 9 minus 3 divided by t squared. So let's see, plus or minus 1, I end up with 0.16228 here. So this is clear what I'm actually saying. It's 0.16628. Plus or minus 0.1 gives me 0.16662. Plus or minus 0.01 gives me 0.16667. And so what are we expecting the limit to be? Well, notice that from point 1 to point 0.1, I end up from point 16662 to 1.6667. As it turns out, if I go lower, I'll just end up with more of these 6's, but I'll still have a 7th. Yes?
Is it because you had to round the last one because it was a 6?
Yes, that's actually the point. And so, as it turns out, this is nothing else but a 6th. If you take out a calculator, put 1/6 in for as a calculator, and it'll give you 16666, whatever decimals you'll have, and at the end you'll have a 7, right? Because it'll round. Is this making sense? So, looking at this, it would seem that it actually is a 6th, right? And the reason why I'm going through this example is to show you why we actually need better ways of evaluating these limits. What happens is if I actually go closer? So, if you did not actually see the fact that that actually looked like a 6th, and you might actually want to say, how about if I actually start looking at things closer? So if I put in 0.0005, I end up with 0.168. Put in 0001, I end up with 0.2. Plus or minus 0.00001, I end up with 0. And from this point on, they're all going to be 0. So what is this actually telling me? What is the limit? Is it 1/6 or is it 0? As it turns out, it's 1/6. The reason you get up zeros is because your calculator at some point is going to run out of digits, and it'll just round to 0. And so that's actually the danger of trying to compute these limits just by picking up random values. Okay? Is this making sense? Everybody understands this? Yes.
Did you say there's an alternate way to do this?
Yes.
Doesn't take as long?
There's actually 2 alternating ways, and you really see why we actually want the second alternate way. Today we're going to talk about the first alternate way, and you'll really see why we would like even a better way of doing that. This is all, mathematics is a exact science. That's the whole point. If you look at the definition we gave, it can't be more blurry to, come up with things. Does that make sense? Why? Because I'm just saying, if I can make f as close as I want to the value of L by making x closer to a, well, what exactly does that mean? Am I talking about this much, or how exactly am I measuring how close I actually need to get? Right? And so we'll see the actual precise definition of the limit, and after I write it on the board, you're probably going to say, I really preferred the word one. But anyway, we'll get to that. So, noticed we talked about the situation, right? So, and I said that we actually will have side limits, but I never actually defined them. So let's talk about what actually a side limit is. So, definition. We write the limit as x goes to a minus of f of x, or an alternate definition, which is not written here, but I'll write it as well, is the limit as x goes to a but x is less than a of f of x, or a third definition, which is actually one thing that I might actually use more than anything else, is x with an upper arrow towards a, in the sense that it goes up to a. I'll probably use this the most, but if I actually slip up and write this, then you actually know what I mean.
So
all those three are saying the same thing. And say the left hand limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be, by taking x sufficiently close to A, but less than A. Which is exactly why I think, why I like to actually write all these alternate definitions, just to kind of like see exactly, right? I just said x gets arbitrarily close to A, but it's less than A. Well, that's exactly what the second definition just says, right? X goes to A, but it's less than A. Is that making sense? Yes.
What is this the definition of?
A left-hand limit. Similarly, there's a right-hand limit definition. Is there any point in me writing it out? Yes.
Oh, okay, so before we were talking about like left to right, the limit from left to right, and this one's from right to left.
No. The original definition was from both directions.
Okay.
So you have to test that coming from both directions you end up in the same place. This is saying, coming from the left, what do I get?
Oh.
And I basically get, a certain value, and if I come from the right, I might get the same value or I might get a different value. What basically we're saying is the following. The limit as x goes to A of f of x is equal to L if and only if the limit as x goes to A minus of f of x is equal to L, and the limit as x goes to A plus of f of x is equal to L. So what we're saying is the first original definition that I put on the board says that coming from both directions I have to end up in the same place. That's exactly what we're saying here. Coming from the left I end up with L. If I coming from the up I end up with L as well, then my original limit is L. Otherwise, if these don't agree with each other, then I actually don't have a limit. Are you familiar with if and only if conditions? Is everybody familiar? Do you understand what if and only if means? An alternative way of saying that is equivalent, which basically says if this is true, then that's true, and also if this is true, then that is true. Okay? Yes?
Can we do an example, like, the last one where we had n and n? Like, how would we write that? If x goes to A minus, x goes to A plus.
So if I come back to this picture, the limit as x goes to A minus of f of x would be equal to capital M, and the limit as x goes to A plus of f of x would be equal to capital N. Yes?
What does the A minus mean roughly?
That's why I wrote all of them equivalent. A minus means x goes to A, or x is almost A, but it's less than A. That's why it's minus, because it's not, think about the fact that it's not completely A. That's why it's A minus. And A plus means it's a little more than A, which means it's a little to the right of A. Does that make sense?
Yes.
So, let's see. To use the same notations that I did before, the limit as x goes to A plus of f of x is the same thing as the limit as x goes to A, but x is bigger than A of f of x. Or it's the same thing as saying the limit as x goes down to A of f of x. Does that make sense? Okay. For instance, one very standard function, and you might have heard of it before, Heaviside function, is defined to be h of t is equal to 0 if t is less than 0, and it's equal to 1 if t is bigger than or equal to 0. By the way, it's not a I didn't misspell it. It's actually that's the way it's written. It's not heavy as in something's heavy. It's actually the guy's name that actually invented it. Heaviside. What is the limit as x goes to 0 minus of h of t? T goes to 0 minus of h of t. Zero. Should I make a graph of it? The graph of h of t looks like this, since you said no. Right? Everybody sees that's the graph? We talked about piecewise functions before. So now, what is the limit as t goes to 0 plus of h of t? 1. Everybody sees that? Yeah? Okay. So now let's see. What do we have as far as homework? 248. Okay, so as far as the homework is concerned, you have problems 2, 4, 8, 10. Problem 2 deals with the first example we did in class. Okay, you're supposed to come up with the average velocity for these, so a certain type of interval, and then part B says what is the instantaneous velocity when t is equal to 1, which means you'll actually look for the end behavior, what happens, kind of like what is the direction of the values going towards. Number 4, I don't know. Should I do number 3? Maybe I should do number 3 so you can see exactly how things work a little better on an actual problem. I skipped the end part of the section at this point because I think this is, as it is, a relatively new concept and you're kind of struggling with it. If I just show you the definition of the limit right now, you will go out of here with your head spinning. If you don't believe me, read the definition on page 31. Okay, so that being said, let's look at a few problems first, and then we can work things out. Your next homework is just section 3, and the intent was not to finish section 3 today because there's so many concepts involved here. So I'm basically going to do the bulk of it today, but we're actually going to talk about some stuff on Friday as well. So and then I don't know if you're aware of this or not. I probably should have said this before, but Monday is off, right? Everybody knows Monday is off? Not only Monday, but it's actually Monday and Tuesday. We don't meet Tuesdays, but nonetheless, both Monday and Tuesday are off because of Labor Day.
So will the homework still be due?
The homework will be due on Wednesday. It's only section 3. That's the point. We're doing part of it today. We're going to do the finish. We're going to finish the rest on Friday, and that's why the homework is only section 3. Okay. So problem number 3. I'm going to try to graph this to the best of my abilities, but we'll see if I'll actually be able to. So you might actually have to follow this on your textbooks as well. So let's see. Actually, what do I need? I need 1 and 5. Oh, okay, well that's not that bad. I guess I don't actually have to worry about too much. So 2, 4. Okay, so this is the graph, again, as I said, to the best of my graphing abilities. So part A, what is the limit as x goes to 1 minus of f of x? Two? So we can follow it graphically, right? The point is, as x gets close to 1, but it's to the left of 1, means I'm coming down on this branch, and I'll hit 1. I'll hit the value of 2, right? Very close to 1. Is that making sense? Okay. Part B. What is the limit as x goes to 1 plus of f of x? Three. Everybody understands why it's 3? Yes? Okay. Part C. The limit as x goes to 1 of f of x. Does not exist. Does that make sense? Sorry? The values are different. So since the values are different, my original limit, my actual limit can't be the same. The limit says, when I say the limit as x goes to 1, this doesn't discriminate if you come from the left or from the right, which means you have to make sure that you know, coming from both directions, you come up with the same answer. Yes? If what is the limit as x goes to 5 minus of f of x? Four. What is the limit as x goes to 5 plus of f of x? 4. What is the limit as x goes to 5 of f of x? 4. Everybody understands this?
Yes.
What is f of 5? Does not exist. Very good. Is this making sense? Again, the most important idea about limits is that we don't care the value of the function at that exact particular point. What we're interested in is what happens in the neighborhood of the point. That's actually what really should transcend from today. Is that making sense? Okay, let's see. What else do we have? We have 8. Problems 7 through 10 say, sketch the graph of an example of a function f that satisfies all the given conditions. You're supposed to do 8 and 10 out of this. You want me to do one of them?
Yeah.
Okay. So how about in the middle, number 9? We have the following. The limit as x goes to 3 plus of f of x is equal to 4. I know the limit as x goes to 3 minus of f of x is equal to 2. I know the limit as x goes to minus 2 of f of x is equal to 0. The limit as x goes to 2 plus,
Wait, yeah.
that's because I can't read apparently. So let's try this again. The first two I think are correct. Trying to read and write in the same time while not actually having it close was confusing. So I got the first two correct, right? The next one was that the limit as x goes to minus 2 of f of x is equal to 2. F of 3 is equal to 3. And f of minus 2 is equal to 1. So we need to come up with a graph. By the way, I should point out that for these particular problems, there is not one universal answer. The answers can vary quite dramatically because the only restrictions we have are at 2 particular points, right? So how do we graph this? Well, the 2 points of interest are negative 2 and 3, right? If I look at 3, what do I have? I have f of 3 is equal to 3, but I have the 2 limits are actually not equal to 3. None of them are equal to 3, right? If I look at the first one, it says the limit as x goes to 3 plus of f of x is equal to 4, which means if I have 1, 2, 3, 4, this is 4, I have that. Does that make sense?
Why is it an open dot again? Oh, okay.
F of 3 is actually equal to 3. If f of 3 was 4, this would be full.
Okay. Yeah, you're right.
F of 3 going to 3 minus, I end up with 2. So that goes that way. And the value of the function at 3 is equal to 3. Does this make sense? Now let's switch back to minus 2. It says the limit as x goes to minus 2 is equal to 2, which should tell us that the limit exists, right? What else do we know? F of minus 2 is equal to 1, which means we have a hole at negative 2, right? So that says that, okay, this is supposed to be full, but I can't seem to, okay? Is this making sense?
Yes.
Yes.
How do we know about both sides of the direction of where the line is coming to?
In what sense? How do we know it's coming decreasing or something? An alternate graph would be,
Or not like,
technically that's not a graph, but anyway, you understand my point? That's why I said they can be a variety of answers in the end, right? This is not a graph because this doesn't satisfy the vertical line test. But anyway, the point is that what you're asking? How do we know that it's coming, which way it's coming?
no, like, say how you got, and you know from one way it's going to
Well, look here. I'm saying x goes to 3 plus, it's equal to 4. Which means as I'm coming down to 3 on the x-axis, my graph comes to 4. So it has to be coming this way.
yeah.
It doesn't matter if it comes from up, from below, from whatever direction it comes. It's to the right of 3 as far as the graph is concerned. Think about a vertical, imaginary vertical line. To the right of 3, my graph comes in this way. It comes in 4. Is that answering the question?
Okay, so my question is, you know the limit from the left, right?
Mm-hmm.
But you don't really know the limit coming from the right?
You mean here?
Yeah.
There is no plus or minus here. This is the limit as x goes to minus 2.
Oh, I just,
Which means this satisfies both plus and minus.
okay.
And they're both coming in the same spot. Yes, the minus, and this is one of the reasons why sometimes I don't necessarily like the pluses and the minuses above there, because sometimes you might be confused and say minus 2 means 2 minus, or minus 2 minus, or something like that, but it's actually just minus to the point. Okay? All right, let's see. What else do we have? 24, 30, 32, 34. Okay. So, everything else from this point on actually requires the definition of a limit. So, as the last part of the class today, I'm actually going to write the actual definition of a limit. So you see how lovely it looks. Bless you. Okay, let f be a function defined on some open interval that contains the number a except possibly array itself. We say the limit of f of x as x approaches a and write the limit as x goes to a of f of x is equal to capital A, or capital L. I forgot to say is L. Sorry about that. Forgot to say that the limit is L, and write that. If for every number epsilon bigger than 0, epsilon is just is a 3 written in reverse, basically. There is a corresponding number delta bigger than 0, such that if 0 is strictly bigger than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Yeah, it's a small letter delta.
Delta is what?
Delta?
Yeah, what's it mean?
This one?
Yeah.
It's the Greek letter D. Epsilon is the Greek letter A, by the way.
Why are we using it?
Because mathematicians really love Greek letters.
So it could just be any variable.
This is actually also known the epsilon delta definition. So in the worldwide, globe, the epsilon and delta always represent the definition of a limit. That's actually the two letters that are always used. So throughout the semester I might change letters in general, but these will always be the same. Epsilon and delta are the standard universal ways of writing things. And if you don't necessarily know how to write them, as I said, epsilon is just the 3 reversed, and delta is just the D with a little bar above. Yes? I'm sorry, say that again?
I said, so the homework from 22 on, is that what we need, right?
Yes. From 22 on, we're gonna use the actual definition to come up with the limits. Yes.
So if we were to start our homework today, how far do you think we could get for
2, 4, 8, 10.
2, 4, 8?
You can attempt 24 if you want. But if you want to attempt that, you have to read example 9 first.
Okay.